Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this video is the equilibrium constant, and the sections in the textbook are 16.2 to 16.3. So here are the learning outcomes. At the end of this, you'll understand where the equilibrium constant, K sub p, originates from. You'll be able to calculate Kp through the Gibbs function. You'll know how an inert or a non-reacting gas affects an equilibrium composition, and you'll be able to calculate the equilibrium composition of a reacting system using Kp. All right, so we're going to derive an equation here, but let's understand first of all what in the world we're trying to figure out with this. All right, so if I have some mixture of gas, like I show up here where I have carbon dioxide, carbon monoxide, and oxygen, the question I want to answer is, what's the equilibrium composition? Meaning, given an infinite amount of time and allowing the system to react, so giving it some initialization energy, what is the equilibrium composition? How many COs am I going to have? How many CO2s am I going to have? How many O2s am I going to have? What are the relative amounts? So there's the question that we're trying to answer here. We're going to derive an equation that's going to tell us, it's going to describe what that composition is for any amount, any group of gases. All right, so let's start with our equilibrium condition that we have. We derived in the previous video, which said if I sum over the Gibbs function times the stoichiometric coefficients, the product of all of those, that is going to equal 0 at equilibrium. Now, the mu here, that's the stoichiometric coefficient. It's going to be minus for reactants and positive for products, because either I'm consuming them or I'm forming them. So some of the signs are going to be a little bit different. Now, this is the Gibbs function, and what I'm going to need to do is I want to know this at any arbitrary pressure and temperature. So that means I need to go ahead and determine what the Gibbs function is at some arbitrary temperature and pressure. And I'm going to do this in kind of a two-step process. And this is similar to what we did like in terms of entropies, because entropy was also a function of temperature and pressure, is I'm going to determine what is the Gibbs function at a particular temperature and at a constant pressure, like atmospheric pressure, P0. And then I'm going to go ahead and calculate what the change in the Gibbs energy is going from P0 to some pressure, and then hold that at a constant temperature. So that's similar to what we did with our entropy. So remember, we had delta S. So we're looking at pure components here. Remember, delta S, if I wanted to know what its change in entropy was, we had Cp ln of T2 over T1 minus R ln of P2 over P1. So we find out the change going from conditions 1 to 2. If we did it at constant temperature, that would be 0. So here was our change in entropy terms. That's similar to kind of what we're doing here, just now we're doing this in terms of Gibbs energy. And so since Gibbs is defined as H minus Ts, we could say that the change in Gibbs energy, delta G, is going to be delta H minus T delta S. And so this is delta G, that's that term right there. And so if I'm doing that at a constant temperature, that first term is 0. So what I have, the second term is just going to be T minus, or delta S. And that delta S term, since this is 0, is just R ln of P2 over P1. So I'm going from P0 instead of P1 now, P0 to some pressure P2. So that's going to go ahead and give me what my Gibbs energy is at any temperature and pressure. It's going to be, the symbol we're going to use here is G to a star. So the textbook's using, this is the standard state Gibbs energy. So that's just a function of temperature, and that's at 1 atmosphere of pressure. And then plus RT ln of P. So there's a change in sign because Gibbs energy is minus Ts, and the term that's left is minus R ln of P2 over P1. And this is the partial pressure, so in terms of atmospheres. So it's at 1 atmosphere of pressure, the partial pressure would be 1. If there's 2 gases in there, it would be 1/2. But that partial pressure term, so it's going to be unitless if it's always over 1 atmosphere of pressure. Okay, so there's the Gibbs energy. That's what we're going to be sticking into this equation right up there. And it's going to have these couple components there. More or less similar to entropy, you can think of it as a temperature contribution and a pressure contribution. So let's go back to this generic equation that we had. Let me clean that up a little bit, just erase a little bit of this. Okay, so remember, this is that generic equation that we used before, where we just had A and B reacting to C and D, and we've got the stoichiometric coefficients of each. And we're going to go ahead and use this generic equation, and we're going to go ahead and plug it into our equilibrium condition up at the top. So this is what we're going to have. So this equation becomes this, where I've added all the products because they're being formed. So C and D are being added. So I've got that term plus that, and then I'm subtracting the reactants because the coefficients there are going to be negative, and so there I've got minus the A and minus the B. So this is just a generic reaction, A to B, C to D. You can do it for anyone. So I've got all of these terms right here. And now what I'm going to do is I'm going to do a little bit of grouping to make this a little bit easier. And so what I'm going to do first of all is I'm just going to define this function, big delta G star, and just for convenience, you'll see why this is going to be helpful. And it's going to be just the stoichiometric coefficients times the little G star term. So since I'm taking that term, that term, that term, and that term, right? I'm grouping those together and calling that delta G. And then what's going to be left are going to be all those log terms in terms of pressure. And so if I was to more or less move those terms to the left-hand side and call it delta G, then what's left on the right is minus RT, and the natural log of these partial pressures. Remember the laws with logs, if I have a log of A minus log of B, it's the same as log of A over B. That's why I can turn into this fraction that I have over here on the right-hand side. Now, one of the interesting things here is that G star, remember, is always at 1 atmospheric pressure, so it's only a function of temperature. Doesn't matter what the pressure is because they're always evaluated at 1 atmospheric pressure. So the thing on the left is just a function of temperature. That means this thing over here on the right is only a function of temperature as well. So even though all I see in here are pressures, it turns out that whole term right there is just a function of temperature. And that makes this pretty convenient. Because what I'm going to do now is define an equilibrium constant, equilibrium coefficient or equilibrium constant, mean the same thing, as a Kp, and I'm going to make it equal to the ratio of these partial pressures to the stoichiometric coefficients, which would be the same as the exponential of delta G over RT. And this, again, is only a function of temperature. So that means, given a particular temperature, I can calculate this, which means I know the relative partial pressures of all these. So back to my original question, I now, given a temperature, I can go ahead and determine what this function is right here, and that will tell me what the relative amounts of all of my gases are. And that's actually pretty powerful and pretty useful to do. Okay, so we're actually going to go through an example just and plug through and see how you can actually do it. So here's the example we're going to do. I've got H2 and O2 reacting to form water. And what I want to know is what's the equilibrium coefficient at 77 degrees Fahrenheit. 77 degrees Fahrenheit is room temperature. It's going to make some of the terms a little easier to calculate here. We'll look at another temperature in just a moment. Okay, so let's remember K sub P and Kp, that's what we're trying to determine. And that right there is equal to the exponential of minus delta G star over RT. Okay, so that means I can go ahead and determine the log of Kp, and the log of Kp is going to be equal to minus delta G over RT. Okay? All right, so big G star. And so that's how I'm going to go ahead and determine what my equilibrium coefficient is. And so here's big delta G star. And that right there is going to be equal to, this is the stoichiometric coefficient of my products. It's going to be mu of the water times G star of the water. Okay? And then I'm going to subtract the reactants, so minus mu of the H2, G star of the H2, minus mu of the O2, G star of the O2. So I have products minus reactants. All right. So now each one of these G stars, the standard state Gibbs energy, G star, well, that's going to be equal to H minus TS. And this is at standard state, so that's going to be S superscript 0. So that's the standard state entropy that we had before. We've seen this starting back in chapter 7. That's only a function of temperature, because G star is only a function of temperature. This is the enthalpy, ideal gas enthalpy. It's a function of temperature. And remember, I can determine that. We did that in chapter 15. That would be HF minus H superscript 0. That's the three components of the enthalpy minus TS0. So a lot of terms, but nothing that we haven't seen before, because we can go ahead and calculate the enthalpy, like we did in chapter 7. We can find our standard state entropy. We can put those terms together. That gives us G star, which is what we're going to put into that equation. My stoichiometric coefficients I have, I've got a 1, a 1/2, and a 1 up at the top. So, all right, so let's go ahead and do that. We're going to find delta G star. All right, so it's going to be my stoichiometric coefficient of the water, 1. And now I've got to put in all of these terms. So I'm going to have the heat of formation of water. Now this is at room temperature, so the H minus H0 terms are going to go ahead and drop out. So I don't have to calculate that, and that'll just be 1 minus T S0, which is this term here. So I'm able to to skip through those terms on this one. And then so that's the reactants minus, sorry, that products minus the reactants. So here's my H2. And heat of formation of H2 is 0. Okay, minus TS0. And that's for the H2. So let's put down, this is of the water, this is of the H2, and then minus 1/2. And this is going to be of the oxygen. Heat of formation of O2 is 0 minus TS0 of O2. Now, the S superscripts little degree symbols here. This one's for water. Then I've got one for H2 and O2. So they're all going to be a little different. Let's go ahead and put our numbers in here. So this is of the water. Heat of formation is 104,040. That's the heat of formation of water. Minus the temperature, 537 Rankine. And then if I look up S0 at that temperature for water, that's 45.1. And now I'm going to subtract the hydrogen. With a coefficient of 1, it's going to be 0 because that's 0 there from the heat of formation, minus 537, and then S0 for that is 31.2. So there's the H2 terms, minus 1/2, 0 minus 537, and now I'm doing the O2, and that I think is about 49, I believe. Okay. So this right over here, this is all big delta G star, so I can go ahead and just plug that into my calculator and calculate what that is, and that becomes minus 98,350, and my units here in English are going to be BTU per pound mole, right? And that right there is equal to minus RU/T/ln of K sub P. This is the universal gas constant because I got this per pound mole. This is going to be 537. So if I go ahead and just solve that now for Kp, the natural log of Kp is about 92. That's a natural log. So then if I take the exponential of that, I find out that K sub P is about equal to 10 to the 40, which is a huge number. It's somewhere between a septillion and a sextillion. I guess we'll just call it a zillion, zillions. Anyway, that's a huge number. So what that means, and we're going to look at this more, when I have large values of the equilibrium coefficient, that's products over reactants. That means I have a whole lot of products and not many reactants. So if I look at my equation, it tells me I have a whole lot of water and not much H2 and O2. However, what's important is it's not 0. There is still some H2 and O2. It's just 1 out of every 10 to the 40th about, to give yourself a ballpark number. So it doesn't quite go to completion, but it gets really, really close. So what that means, if you go back to that previous lecture where we were talking about the Gibbs energy, and this was a function of my reaction going from all H2 and O2 to water, and G is going to have a minimum. It means it goes down here, and then right at the end, it starts to go up just a teeny bit. So there's my equilibrium concentration, not quite to the end, but really, really close. There's always going to be a minimum somewhere in the middle for all reactions. All right, now let's go ahead and do the exact same problem, but now we're going to do it at a higher temperature. So there's going to be a couple extra terms. So again, just to remind you, we have delta G star, and that right there is going to be equal to stoichiometric coefficient of my products, G star minus the reactants, which was H2, and minus that of the O2. So that didn't change. It's the exact same thing that we had before. But now we have G star, which is, remember, that's going to be H minus T S0. Now this H right over here is going to be at 3240. And so this is HF minus H0 minus T S0. This right over here is now at 3240. So we're going to have a couple extra terms that we need to go ahead and put in. And what I'm going to do to kind of show you just another way to do it, let's go ahead and move to EES to go ahead and solve this problem. Okay, so here I've got the problem in EES. And so let's go up here. Let's look at first an important thing. I'm setting my unit system to an English. I'm setting it to BTUs, temperature degrees Rankine. I'm doing my pressure in atmospheres. And I'm also setting it equal to molar units. Okay, so here I've defined my temperature T1 at 3240. That's the temperature I'm trying to use. And now, this is actually pretty straightforward in EES. I'm going to find G of water. Now, first of all, we mentioned there is no Gibbs function like there is enthalpy and entropy, but it's pretty simple. Remember, G is just H minus TS. So G is the enthalpy of water minus T times the entropy of water. And I'm doing Enthalpy at just temperature, it's ideal gas. And then I need to give it a temperature and a pressure, even though it's an ideal gas. For entropy, pressure is 1, because I'm doing this in terms of atmospheres. Right? And so this is the standard state entropy by giving it a pressure of 1. So I do G of H2O, G of H2, G of O2, just kind of a copy-paste pretty quick. And now I'm going to find that's big G, that's my big G star, and it's just equal to G of water minus G of H2 minus 1/2 G of O2. There's stoichiometric coefficients of 1 for the water and the H2. And then I can go ahead and say, well, find the natural log of Kp is minus big G over RT. So it's pretty straightforward. If we go ahead and solve this now, here I go, and I find my big G at minus 63,000, and Kp is 18,700. Okay, that still seems like a big number, but it's nothing like 10 to the 40th. No more the septillion, sextillion type number. Now we're just down at 18,000, which means that we don't have as many products at a high temperature. And what you can learn from that is that exothermic reactions, which burning oxygen and hydrogen is very exothermic, exothermic reactions, if you raise the temperature, get driven toward the reactants. And one way to think of it is from like Le Chatelier's principle, where we're producing heat, we raise the temperature, we're going to drive it back toward the reactants. Okay? So it's a lot easier to solve in EES, but I think it's good to see it both ways. Okay. We're going to talk just a little bit more about the equilibrium constant. So again, here's the definition of equilibrium constant. We had it for our general reaction A, B, C to the D. And something else you can remember, these over here are my partial pressures. And so the partial pressure for some gas, P sub I, is the mole fraction times the total pressure. I can write that way. And the mole fraction is the number of moles over the total number of moles that I have times the pressure. And so I can go ahead and substitute in the right-hand side into that equation, and you end up with what initially looks a little bit more confusing, but we're going to find it pretty useful. So I've collected all my mole terms over on the left here. So now N is the number of moles of each constituent. I have my total pressure over the total number of moles, and then I add up all my stoichiometric coefficients. And I'm adding the products and subtracting the reactants, because products are formed, reactants are consumed. And so this was for my general reaction A to B. Let's just go ahead and write a more general form. And notice what we're doing is we're multiplying all the products. This big capital pi means products. I'm multiplying over all the products. That's what sub P means there. The number of moles to their stoichiometric coefficient. And the bottom is the products of all the reactants times their stoichiometric coefficient. And now I have the total pressure of the system over the total number of moles in the system. And delta nu is the change in stoichiometric coefficients. Number of products minus the number of reactants. Okay. And this equation is kind of nice because there's some interesting features we can see from it. And the one I want to look at here is, imagine I've got this mixture of gas. I've got A plus B going to C. And so the stoichiometric coefficients on each one of those we'll say is just 1. So 1A plus 1B goes to C. And that would be like carbon monoxide, anyway, I won't put it in here. But just A plus B going to C. And so the question is, what if I took a whole bunch of D and put it in there? D is an inert gas. It doesn't react with A, B, or C. I'm just pumping a bunch of D in. And my question is, do you think it's going to affect the number of A's and B's and C's that we have? And it turns out that it is, because if I start adding a bunch of D in here, I'm going to draw in some D's in fact, right? To put a bunch of D's in there, I'm increasing the number of moles. I'm increasing N total. And so if I look at this equation, I'm increasing N total. Now, what's delta nu? Delta nu is the products minus reactants, so it's going to be the 1 in front of the C minus the 1 in front of A, 1 in front of B. So delta nu is minus 1. So this coefficient is going to be minus 1. So that would be the same as saying N total over P to the 1 pressure. And then I have all these terms right over here being multiplied by that. Now, that means that if N total is going up, that term's going up, this term right over here has to go down, right? And so if it goes down, what that means is I've got to go ahead and get rid of products, right? Because that's in the top. I want that to be smaller. I've got to get rid of some products. So this is what's going to happen. If I add a bunch of D, a bunch of these C's are going to get pushed back into A's and B's. And now I'm going to have this new composition, less C, a whole lot more A and B simply because I added a bunch of D. So D isn't reacting, but it affects the equilibrium composition of the mixture. Okay, let's go ahead and do one final example. And here what we're going to do is we're going to determine the amount of H2 that dissociates at 8 atmospheres of pressure and 3,200 Kelvin. Okay? So here's the reaction that I want. Dissociation means break apart. So I have H2 and going to 2H. And so what I want to know, I'm going to write this like an equilibrium condition with a double arrow. It says, how much H2 do I have versus of the H? So I put a bunch of H in a box, raise it up to 3,200 Kelvin and 8 atmospheres of pressure. How much H2 is going to, or how much H2 is going to break up into H? So there's the question that I want. All right. And so remember, I'm going to use the equilibrium coefficient. And so the first thing I'm going to do is I'm going to look up what the value of Kp is. And Kp is listed in the table in the back. And so if I look up the natural log of Kp for this reaction here at 3,200 Kelvin, that value is minus 2.534. All right. So that's the natural log of Kp. If I took the exponential of that, it's going to be 0.07934. So there's what Kp is. Remember, Kp is equal to partial pressure of my reactants, which is going to P sub H, partial pressure of just the pure hydrogen, to their stoichiometric coefficient squared over the partial pressure of H2, stoichiometric coefficient of 1. So that tells me the partial pressure of H over the partial pressure of H2 for an ideal gas mixture. That's going to go ahead and give me, to tell me how much H I have or how much actually dissociates. So again, this value of Kp, these are out of the table in the back of the book. I think it's A26. They list values of Kp as a function of temperature for various reactions, and then you look up this reaction right here. Oops, I misspoke here. Let me take a quick break here to show you. This is table A28, and this is where we're going to get the K sub P values, or the equilibrium constant values. And so this table here lists various reactions up here at the top, and that's all as a function of temperature that we list over here on the bottom, or on the left-hand side here. So in this problem, where we're trying to find this at 3,200 Kelvin, we're going to go to 3,200 Kelvin, and then we're going to look across, and here's our value of minus 2.534. And note that these are giving natural log values. So the natural log of Kp is minus 2.534. So that's where you get it. So again, this is table A28. Okay, so this is the reaction that's going on. But let's think of the actual system. Is I essentially, let's say I start off with 1 mole of H2. Okay, I have 1 mole of H2. I take it up to this temperature and pressure. So what I'm then going to have is, well, I'm going to have a mixture of H2 and H. And how much am I going to have? Well, I'm going to have 1 mole minus however much dissociates. I'll call that X. That's the amount of H2 plus, and then how much H? Well, for every X of H2 breaks up, I'm going to get 2X of H. So here's my new equilibrium composition right over there. 1 minus X of H2 and 2X of H. So let's go ahead and use our Kp. Remember, Kp is the summation of the number of moles of product to their stoichiometric coefficient over the number of moles of reactant, their stoichiometric coefficient, P over N total, all to delta nu. So you can go ahead and use that reaction, and let's go ahead and plug in our numbers. And so here we just have simply one product and one reactant. So how many moles of product do I have? Well, I've got 2X, right? So this is in my equilibrium composition. I have 2X, and then it's raised to stoichiometric coefficient. That's a 2 right up there, so it's 2 squared. Reactant, so I've just got one reactant, which is the H2, and the number of moles I have at equilibrium is 1 minus X, and that's going to be the 1 power, the stoichiometric coefficient. And the pressure was 8 atmospheres. And now what's the total number of moles I have? Well, I have 1 minus X of H2s and 2 X's of H. So I have 1 minus X plus 2X. And that right there is going to be equal to delta nu, which is going to be 2 minus 1. All right? And that right there is all equal to Kp, or 0.07934. And so this is a nonlinear equation, but I can go ahead and solve it. It's an equation solver can solve it. You can use Wolfram Alpha or EES can use it. And if you do that, you find out X is about 0.05, which means that 5% of the H2 is going to dissociate at a temperature of 3200